In section 10.2, we learned how to test hypotheses for a population proportion. So we assumed some proportion was true, and then we used data to test it. Now we're going to take that same 6-step process and we're going to apply it to a different parameter, this time to a population mean, mu. So you're going to assume that the mean is a certain value, and then you're going to take your sample data and test that. All right, and you can see here it follows a very similar structure to the other hypothesis test, but there are some differences and we want to look at them. The first thing we want to look at is the requirements. So it still needs a simple random sample, just like testing for proportions. We always need random samples in this course. And then we need an independent sample. Now, if it's sampling with replacement, this is not a problem, right? Just toss the coin again or whatever. But if it's sampling without replacement, you need your sample size to be less than 5% of your population size. That's one of the conditions of the central limit theorem for sample means, and that is true here. And then we need that the distribution is normal. Now in section 10.2, we could accomplish that with n times p times 1 minus p greater than 10. But in section 10.3, that's not one of our options. It either has to be given to us or in a graph, right, a normal probability plot, or we have to know n is greater than 30. Now let me go back just so you can see. This is the hypothesis test for a proportion. Proportions need n times p times 1 minus p to be greater than 10. Okay. The other two caveats or the other two requirements are still the same. But here, just 30 is plenty. And that's a rule of thumb, of course. That's not always true that 30 is enough. 30 is enough as long as you have no outliers. And it gets more complicated with that as you move on in statistics. But for our course, for our purposes, greater than 30 is fine, and we would like it to have no outliers. All right, if that's the case and we've met those conditions, then we can run the 6-step hypothesis test. So we'll have to have a null and alternative hypotheses, and these should look familiar because they're very similar to the ones for proportions. Proportions had p equals, right? So p equals p0, p not equal to p0, p equal p0, p less than p0, and so on. Whereas the 0 is the 0 from the null hypothesis, p naught, if you will. So here we have h naught, h sub 0, is mu equal to mu sub 0, right? Where 0 is the value you, or excuse me, mu 0 is the value you assume it to be. So remember this from chapter 8. We kind of assume some parameters about the world, and then we're going to test them using the steps below. Then we have our alpha level of significance. That's the seriousness of making a type 1 error. And for our purposes, it'll almost always be given to us in the problem, which is fine. Then we're going to find the test statistic T0, and then that's a different formula than you've had before. And then now because this is a t-test, because this is about the mean, you don't have, you don't have your standard deviation and mean that you had from the proportion ones. In other words, we don't get to use the z curve. We have to use the t curve, which remember from chapter 9 is kind of a weaker version of the z curve. I mean, it looks similar, but it's actually not the same at all. It has fatter tails. It's got a shorter center. It's more spread out, in other words. Right, so there's the two-tailed picture, the left-tailed picture, the right-tailed picture for the classical method. Or we could use the p-value method, and the pictures look the same, but they're not, because the p-value method uses the test statistic found in part 3 to label our axes. All right, then in step 5, we have to make decisions, either to reject or not reject the null hypothesis, either based off of the classical method being less than or equal to, or less than or greater than the critical values, depending on which kind of problem you're doing. Or, I love it, the p-value method, is your p-value low? If your p-value is low, you reject the null hypothesis. I like the p-value method. It's a little bit simpler. And then we make our conclusion, write our conclusion following the instructions from 10.1 that we've seen a long time ago. We saw a long time ago. Okay, so let's just start this problem. We won't have enough time to finish it, but let's get going at least on the requirements part. So according to the US Mint, quarters weigh 5.72 grams. I shouldn't say weigh. Technically, it's have a mass. Weight is not exactly the same thing as mass, but all right, so have a mass of 5.72 grams. A researcher is interested in determining whether the new state quarters have a mass that is different than the old value of 5.72 grams. So he randomly selects 18 state quarters, measures them, and obtains the following data. And there they are. So that's 18 different state quarters masses. Mass, of course, is the amount of stuff, if you will, that you have in any particular quarter. Weight is actually that mass affected by gravity. Take a physics class, they'll explain it all to you, it'll be fun. Okay, so are each of the following requirements for, are each of the requirements for conducting a hypothesis test satisfied? Explain. So I typed up what those requirements were, and I'm just going to rewrite them. I don't actually want this portion. We're going to write over that. So did we have a simple random sample? Yes, right? It was given that the sample was random. I think it's stated in the problem somewhere. Yep, randomly selects right there. There we go. So given that it's random. Now, is this an independent sample? Okay, well, we're not sampling with replacement here. So they didn't put the quarters back and allow us to reuse them. So if that's the case, then we need our sample size to be less than 5% of our population size. But the population size here is all the quarters on the planet, right? All the US quarters. And 18 is well below 5% of that. There we go. So I just typed that up. So we are sampling quarters without replacement, but it's okay because n, little n, which is 18, is far less than 5% times all the quarters in the world, where n is the number of quarters in the world. There, just to make that a little bit clearer. Little n is less than or equal to 0.05 capital N, and that's because 18 is less than or equal to 0.05. Capital N is the number of all the quarters in the world, right? And we are well below that 5% threshold. All right, now are the data normal? Is the distribution normal? Well, it has to be given to us or in a graph, or we need n to be greater than 30. Well, we definitely don't have greater than 30. That's out, right? So because we only have 18 here. And it doesn't say anywhere up here that it's normal, right? That the distribution is normal. So we need, given is out, n is greater than 30 is out, and that leaves us a graph. But luckily for us, they gave us a big graph right here. And that shows us that the data distribution is normal. There we have it. So the normal probability plot shows that the population distribution is normal, which is what we need. So that gives us our yes. We can also surmise that there are no outliers from the graph too. Yeah, I don't need to also and too. So we can also surmise there are no outliers from the graph, though a box plot would be a more accurate way to be sure of that. So box plots, box whisker plots from section 3.5 really accurately show us whether there are outliers, but you can kind of see when you look at it that there's no point that's out of whack with this, right? They're all pretty much following in a line. Outliers will tend to be outside of the boundary lines, and they cause the distribution to have some issues. All right, we're going to stop right there, and then I'll pick up in the next video for actually conducting the hypothesis test.